Hello, everyone. I'm Benjamin. Currently, I work as a software engineer at EngFlow, where we're working to make everyone in the world have fast builds. And in this talk, I'd like to talk about a concept which gets thrown a lot around in the Bazel community and the build world more generally, hermeticity. And I'd like to explore this concept with a few different stories, which all revolve around hermeticity. So this is a not a talk with a strong driving central point. I just want to kind of broaden the knowledge people might have about hermeticity. So let's get started. And the first thing I'd like to do is begin, as one might, a mediocre essay one's writing in secondary school by giving a dictionary definition of hermetic. So the gold standard, the Oxford English Dictionary, defines hermetic as an adjective that is relating to the airtight closure of a vessel, especially a glass vessel, by fusion, soldering, or welding. So that's not immediately applicable to software builds, but we will be getting to that shortly. First, though, we'll note that the definition is not the only thing the dictionary has for us. The OAD also tells us the etymology of the word. And I'd like to tell you about the etymology of hermetic, since it's a surprisingly rich story. But before even I do that, I'd like to say a few things about false hermetic friends. So the word hermetic shares a spelling and sound similarities to a few other words in English, and that's partially because of vowel mergers in a few English dialects. But these false friends can cause confusion and give us a false sense of where the word comes from. So, first of all, we have this guy in this slide here. So this is Charles Hermite, a French mathematician from the 19th century. So he was a pretty productive fellow. He proved that Euler's constant E is transcendental. It's not the solution to any algebraic equation over the rational numbers. And he also lent his name to the mathematical adjective hermeticity, which is suspiciously close to hermeticity. However, hermeticity refers to self-adjoint linear operators, not related to air-gapped glass vessels. We also have this other one, hermits. So sometimes someone who's a whole lot less excited about build tools than me has overheard me being enthusiastic about hermeticity and thought I was talking about hermeticity, a state of seclusion away from the demands of society, aka a hermit. So hermitage has a long history, especially as a religious practice. In 18th century Britain, though, it took a particularly strange turn. And it was fashionable at that time for wealthy landowners to employ a garden hermit on their vast estates. And the garden hermit would live on the grounds in a hermitage, as is romantically portrayed here. And the garden hermit would serve as visual entertainment to the owners and their guests. And sometimes the hermit would even dispense advice and counsel to guests that sought him out in his hermitage or rookery. On the surface, hermits are pretty unrelated to build tools. I think, though, that we may want to treat our build actions a little bit more like garden hermits. Keep the compiler and its embarrassing to undefined behaviors off in the garden, and occasionally feed it little bits of C++ when we're far away from polite company, just in case its output is particularly nasty. But anyway, after those false friends, we can finally come closer to the real origin of the word hermetic, and that is the Greek god Hermes, represented here on the left. So Hermes was the swift herald god for the Greek gods. He had winged sandals for that purpose. And among other things, incidentally, he was the protector of orators. So I'm going to ask his blessing for this talk. So it's pretty clear. You can see the relation between the words hermetic and Hermes. But that's actually not the full set of the etymology. We also have to deal with the beaked character on the right here. And that is the Hermes' Egyptian counterpart, the moon god Thoth. So in Egyptian mythology, Thoth had many weighty responsibilities, including inventing writing, judging the hearts of newly deceased people in the underworld, and maintaining the stability of the entire universe. Um, so it must have been a tough job. So how these guys come together is that in about 200 years before the Common Era to about 1400 years after that, numerous philosophical and scientific and religious books and tracts were written, and they are attributed to a fusion of Hermes and Thoth. And this fusional author was called Hermes Trismegistus. I do not claim that is the correct Attic pronunciation, but it will do the job. Hermes Trismegistus means Hermes the thrice greatest, which is one of the greatest appellations you could wish for. The collective works of writings which are being attributed to Hermes Trismegistus is known as the Hermetica. And one of the main things that the Hermetica is interested in is alchemy. So this is the sort of pseudoscientific processes of turning lead into gold or creating the elixir of life and other kind of fantastical things that people thought you could do with chemistry. And one of the key pieces that the Hermetica advises you need to do alchemy is an airtight glass container. And so that is a hermetically sealed container. And so that finally explains the origin of the word hermetic. And but by the way, the Hermetica and alchemy are a really rich source of names. And if you're looking to create something new in piece of software in the build tool world, I really recommend looking there. I'm very much looking forward to the next sandboxing technology called Trismegistus. I'll have high expectations, of course, for it. So after that historical diversion, we can finally come to the point. The definition of hermetic for software builds. A hermetic build is one that always returns the same output by isolating the build from changes to the host system. I took this definition from Bazel's documentation, and that documentation page has a whole bunch of information about hermeticity. So in addition to this definition, it discusses the benefits of hermeticity, such as parallelism, security, and improved debuggability. An implication of this definition is that the dependencies of a build setup are completely understood by the build tool and consequently the humans who wrote it. To me, that is the heart of hermeticity. Leave nothing implicit. We can also think of the sources of non-reproducibility, such as builds depending on the current time or absolute paths. We can regard those things as potential build dependencies. Then the goal in making our build hermetic and reproducible is to eliminate all these unwanted dependencies so that our builds are hermetic and reproducible across different users, time, and machines. The Bazel world is, of course, not the only community interested in hermeticity for builds. A major force in the wider open source universe is something called the Reproducible Builds project. Here, reproducible is basically a synonym for hermetic. The Reproducible Builds project is closely related to several Linux distributions, and one of its main projects has been making package builds in various Linux distributions reproducible. Since what Linux distributions package encompasses so much software in so many different languages, build tools, and conventions, the Reproducible Builds project has had a large impact across the open source world. The project has developed tools and documentation aimed at finding and squashing systemic sources of non-determinism in build tools. One of my favorite tools from the Reproducible Builds project is a command line utility called diffoscope. Diffoscope is what one uses to debug why two build outputs that are supposed to be the same are different. So, of course, we've had textual unified diff tools for a very long time, but diffoscope extends that to all sorts of binary and archive files because those are commonly the outputs of build steps rather than easily to diff text files. For example, on this slide is an example of diffoscope detecting the difference between two strings in an object file embedded inside of a static archive. It's much easier than staring at a hex dump, I'll tell you. And I've used diffoscope many times to debug non-deterministic Bazel build actions. So if you have that problem, I encourage you to check it out. Another major tool in the build world today is Docker. And unlike diffoscope, I can't really muster unmitigated enthusiasm for Docker. Docker is presented as a solution to a smorgasbord of problems, and it does address some of them quite well. For instance, Docker has done a lot to promote the wider use of Linux containers and their isolation mechanisms. It's also helped a lot to reorient developers' abstractions to emphasize an application-centric rather than a host machine-centric development and deployment workflow. More specifically, in the world of local development, Docker has largely alleviated the infamous works on my machine problem. To call a build done in Docker hermetic, though, I believe is quite a stretch. Because Docker makes it really easy to build multi-gigabyte, non-deterministic images with a huge number of unknown dependencies. To drill in on those problems, let's look at a really simple but Docker file with a bunch of representative problems. The first line here directs Docker to base the image we're building on an image from Google's distro-less container project. That's fine, but this from line does not specify a particular version of the image. Instead, it opts to use the latest image tag. That tag is updated whenever a new version of the image is pushed, and that means the final image that we're building depends on the state of the image server at the time that the Docker file is used. Similarly, Docker makes it easy to download arbitrary blobs from the internet and add them into the image. The URL in this highlighted line at least has a version number, which is more than can be said for the from line we were just looking at. However, the add line is relying on the good graces of the host it's downloading from, example.com, to modify releases once they're placed on the web publicly. So even if the example.com admins are very careful and they only practice immutable deployments, hackers of example.com could replace the archive with whatever malevolent software they desire, and the Docker file would be none the wiser. The software could also just disappear too if the host example.com goes out of business. Finally, in Docker files, we have the ability to invoke arbitrary commands, and I think the problem with non-reproducible is fairly clear here. But even if your program is very, very careful to be deterministic and reproducible, it's very tricky to produce bit by bit identical results. For example, writing files will generally update file system metadata with the current time. So that means even this simple command, which is just writing a static piece of data into a file, still is going to cause timestamps to be written into the image. And commands that reach out to the network repeat all the pitfalls of the add command that we were just talking about. And so consequently, most of the commands that we'll find in a Docker file are really not rigorously reproducible. The conclusion of that is that once you have created a Docker image, there's no guarantee you'll ever be able to get the same one again. There's a workaround for this problem, though. We'll archive whatever image we've created and remember its cryptographic hash. When we want to reproduce the image, we'll just go and download the archived one and check if it matches a hash. Presto, it's technically reproducible. I call this trick stash and hash. It works fine until we need to change one line in the middle of the Docker file and can't create a new image without including many other unintended and perhaps undesirable changes. Hermeticity isn't the only desirable property subverted by sloppy Docker files. It's easy to create images that are made of software with unknown licenses and completely unaudible, which makes security teams pretty nervous. So while Docker has been in many ways a boon to those of us concerned with builds and build tools, it doesn't replace discipline and having a clear understanding of one's dependencies. To contrast with stash and hash, let me sketch how I dream of development environments working at tech companies large and small. Many companies have complex provisioning processes that must run on developer machines before any coding can start. I only want to require two dependencies: Bazel and some version control system. To get started, a developer installs Bazel and checks out the working copy of the company repository. So here I admit that I am a monorepo partisan, but the scheme actually doesn't depend on you only having one repo. Uh, then, once they have the repo in Bazel, those are all the steps they need to do. Using Bazel, they can build and test any code in the repository. They don't need to know anything about language specific package managers or special build tools or install anything on their system. Hermetic toolchains and sandboxing ensure that they get the same result as any other developer and that anything they've installed on their system does not affect the build. It's not just developers that enjoy a simpler setup with this scheme. CI machines don't need to run any complex long provisioning system either, and applications can be deployed with minimal containers. Now, this is just a dream, of course, and there's many places where this will collide with reality and have to be fudged a little. For instance, forcing language-specific package managers and compilers to behave under Bazel's constraints is often a long slog, although it's been done for many of the most popular languages. We must also consider questions like what happens if people are using different operating systems and how are system level dependencies like GPU drivers or kernel extensions handled. But despite the inevitable implementation kinks, I believe this is a glowing cynosure that we can all be happy heading towards. A last hermetic topic that I like to touch on is the construction of a hermetic and reproducible toolchain for a language. This is the sort of tool chain that would be useful to implement my Bazel dream, as shown in the previous slide. And a few modern languages, most notably Go, have this out of the box. So we're going to talk about one where it's a little bit harder, C and C++. And this is actually quite a fraught history. But let's talk more specifically about what we want out of this hermetic C++ tool chain. Okay, so we're going to build our compiler from source. And obviously, to do that, we're going to need some sort of minimally functional host compiler that already exists in order to do that. But we want to be able to reproducibly produce our compiler from a host bootstrapping compiler. We also want any artifacts that our compiler produces that need any runtime libraries. We want those runtime libraries to be reproducible. And we're going to assume Linux for simplicity. And the reason that it's simple is that Linux is special among modern operating systems in that the syscall interface is stable and not just the interfaces of native system libraries like libc. So that means that one can ship a completely separate user space compatible with any Linux distribution. We're going to be seeking to keep our runtime libraries completely separate from any system of their system counterparts. Our runtime libraries will only talk directly to the kernel, and this prevents any breakage if the system libraries change. The compiler itself will be linking our independent set of runtime libraries, which completes the isolation of the toolchain from the system. So we've been talking a little vaguely about compilers and language runtimes as two components, but we need to lay out the specific constituent parts a little bit more specifically. The first thing that we probably think of in a toolchain is the compiler, so GCC or Clang. But we also need some utilities to manipulate binary files. So most importantly, this is the assembler and the linker. So there's GNU implementations of those, which are widely used, and also LLVM has newer reimplementations. So there's this toolchain of components, and then finally, there's runtimes that the compiler products link when they're running. So in the C world, the most important one is glibc, which provides the C standard libraries. Compilers usually provide a runtime library too. For GCC, there's one called libgcc. And C++ has its own standard library too, so libstcc++ or libc++. Keep in mind, though, there's not any clear dependency hierarchy between these components. The compiler is usually a C++ program too, so it needs a glibc and a compiler runtimes to work. And those, of course, need a compiler to be turned into object code. Now, how do we actually go about building all these toolchain components to our exacting reproducibility and hermeticity standards? This is an issue where the long history comes in. And part of that history is something called cross-tool. So this may be a term you're vaguely familiar with from Bazel. And in Bazel, it refers to the kind of arcane system for configuring C++ tool chains. And that used to be a protobuf that you had to write, and now the protobuf has been turned into Starlark. But before it was a custom declarative language for generating compiler flags, CrossTool was a script written in the early aughts by a guy named Dan Cagle. And the script was for building GCC cross compilers and their related runtimes. With a mere few thousand lines of shell, CrossTool automated the previously fragile process of creating GCC tool chains for various architectures. Dan's work has been going strong in this project, which still exists today, called CrossTool NG. And CrossTool NG is kind of a Swiss Army knife custom toolchain builder. You select what versions you want using a very sophisticated configuration system in the target platform, and then hit go, and target CrossTool NG spits out a toolchain after a few hours of compilation churning. Of course, the original CrossTool proved to not be customizable enough for everyone. Google, in particular, developed its own version to build something called Gertie, its internal C++ toolchain and runtime environment. We know about this, funnily enough, due to the Google Search Appliance. What is the Google Search Appliance? Well, if you were a large company before about 2010, you could buy all this yellow box pictured here, and then you could go stick it in a rack in your corporate data center, and it would use Google Search Magic to index all of your company's internal documents without anything ever leaving your network. So very enterprise secure. Apparently by 2016, though, the cloud felt sufficiently safe for enterprises, so Google ended up killing the Google Search Appliance. So it only lives on as an antique now. A delightful consequence of this being a physical device, though, was that the GPL forced the release of much of the open source software in the Google Search Appliance, and in addition, the tools that were used to build that software. And of course, the software is naturally hosted on another discontinued Google service, Google Code. But anyway, if you dig through the archives in Google Code, you can find a script called buildgertie.sh. This appears to be Google's fork of Dan Cagle's CrossTool script to build Gertie. So I've talked about CrossTool NG and Gertie build as forks of this CrossTool script, but turns out this is not the only public one you can find. There may be many more hidden away in proprietary code bases that we don't know about. But at some point, I needed to make a script like this, and neither CrossTool NG or the original were doing it for me, so I had to make my own script. And when I did that, I had to make this awesome ASCII art diagram at the top of my script showing the heritage of it. And I kind of enjoyed that because it felt like I was joining a rich software engineering tradition by writing this kind of shell script. So what are these shell scripts like actually doing, though? Well, it can be summarized as just compiling everything over and over again until we get something that's reproducible enough. And we can think of that in several different stages. So in the first stage, we just have the host bootstrapping compiler, and we have the source for our compilers and tools and runtimes that we're going to build. And we use the host compiler to build all those things. And the goal of that stage one is to get us a roughly working toolchain that we can use to recompile everything in stage two. The output of stage two is assumed to be good because it was compiled with a trusted compiler. In stage three, we do the whole compilation once again to ensure that the toolchain executables are linked against the final runtime libraries and to check the determinism of the build process. We could even make a stage four where we run the stage three process again to make sure we get the same result if we were particularly paranoid. It's not all that complex conceptually, but I have to say, when you're writing the script, it sure feels like you're in the weeds because at various points in the script, you have to keep track of which headers from a particular stage and which binaries from a particular stage you are supposed to be using in a particular step to build another stage. And it gets quite convoluted for a human to keep track of, but it's a fun exercise. And that's all I have in this talk, folks. Thank you very much for listening in. I really appreciate your attention, and I sure hope I'm able to see you all in person next year. So hermeticity is very good for build tools, but it's not so good for humans, and I miss the face-to-face interaction of a conference. So until next year, bye bye.